All right, so we were talking about, I actually brought the last two slides from previous class, so it actually helps us to know where were we and what we were doing. I was talking about components of a robot, apparently, which doesn't make sense. I'm glad I just saw it. Components of a robot. Right? Um, Link joint. I'm not going to go over definitions again. You already know what's going on there. I just wanted to have another look at two important joints that I said we're going to be focused on. Everything else, we just use those two joints to describe any type of other type of motion or manipulator or the links connection, link connections. We are going to use those two joints, revolute joint and prismatic joint. Right? We said revolute joint is basically the joint coordinates an angle. We define the motion for that joint using the angle of rotation, how much it rotates. We can think of it as theta, alpha, whatever parameter used to define the rotation. And we said axis of the joint is basically the axis passing through. You can think about it as a right hand rule. When you have a rotation, your thumb shows the axis of that joint. All right, so any rotation in each direction, the axis is just passing through the joint. And the second one is prismatic joint, right? And we said joint coordinate is basically the translation. We can think about it as two sliding, but sliding in just one direction. Uh, as that joint, so pretty, I guess, it's straightforward. If you look at the schematic of the joint, is we represent that with P. Keep these two in mind: R and P, revolute represented by R, prismatic represented by P, because we're going to use these to define robot classifications. That is one type of classification that is based on the geometry of a robot arm. So these two links, right? The axis, remember where the axes are, remember how they move, and R and P basically stand for their names. Other ones are listed there, but as I said, we barely are going to touch those types of joints. We just represent everything with revolute and prismatic to make things more clear and easier to follow. I defined other parts of a robot. Obviously, we start from joint. We look at the manipulator. We talk about the wrist, I think, one or two classes, and the factor a little bit. Actuators and sensor, we'll see how things go. And for some reason, I just went from color green to color red, listing these components. But this tray is basically, red tray is the continuation of green 2. I don't know what happened there. All right, so what I want to do today is I want to define some common, introduce, better to say, not define, some common robot configurations. Right? You can classify robots in so many ways. The way they are controlled based on their actuators and sensors, based on their end effectors, based on the tasks they do. And you talk to different people, definitely you are going to get so many types of classifications. This is also not a very closed field. Things are changing. Probably 50 years ago, 60 years ago, I don't know, don't quote me on this, but maybe there was no talk about an unmanned vehicle, but now we have that as part of robotics. So things are changing, classifications are changing, but within the scope of our course, we can actually come up with a relatively straightforward way of classifying robot arms. Again, that's what we're going to be focused on. Remember, first generation of robots, these are fixed. So that's what focus. That's where our focus is for this course. So I'll do basically robot classification using the geometry. All right, and I think that's probably the most related way of classification, but considering the course we have and the scope of what we're going to cover. So we can put it under robot classification. Right? You can think of a robot arm, as obviously a set of rigid bodies, those links that we introduced, connected together using joints, right? Which basically form the manipulator along with a bunch of other structural elements in a robot arm. So think of that. Think of a robot in that way. And as I said, we are just going to introduce everything in terms of two joints. Joints can be revolute joint or prismatic joint, and any other joint can be represented using these two joints, right? And it can be a combination, right? It can be modeled as a combination of these two joints. So, following that, I'm going to define three particular configuration, or I would say three ways that two adjacent joints can be modeled or can be set up, right? Two joints next to each other, possible configuration for prismatic and revolute joints when they are adjacent to each other. So let me put a few things here before I get too carried away. So you can say there are, let me see if it's this way. There are different, there are, just to state the obvious, there are different ways of classifying robots. Here we use the geometry and I would say configuration of joints to define some common classes. Some common classes. Now, as I said, joints, I'm going to repeat here, joints can be either revolute, present with R, or prismatic, present with P. And any other joint can be, well, let's just do it this way, the two separate things, can be modeled as a combination of these. And you will see that throughout this, well, I guess to these joints. So let's define three terms, right? Three possible way of P and R, prismatic and revolute joint, can be adjacent to each other, or the common ways that you will see in robotics when we're dealing with industrial robot arms. That and these are defined, or these three types or three possible configurations are based on the way the axes of these joints I would say stand, or the way these axes are with respect to each other. This is the best way I can put it. So the first one is parallel, and those, I'll see if I can do, I think that was a good parallel. Parallel, and we represent that with two vertical line to show that this is parallel. Now, when two joints are parallel, remember we're talking about two adjacent joints. Right? Let me just add it here. Maybe I want to make sure that things are clear. So two adjacent joints, I'm talking about P or R, can be parallel two vertical line. What are two parallel joints? Well, when joint axes are in parallel, simply those joints are in parallel. So just that's it. So joint, in this case, when we have parallel configuration, we're saying basically joints or joint axes are in parallel. What I'm trying to say, think about two revolute joints. Right? If you have one revolute joint, let's say this way, we represent revolute joints with a kind of cylindrical shape, and the other one this way, then the axis of this one is this, and the axis of this one is this. So they are in parallel. You can think about one revolute joint and one prismatic joint. Let's say like this. The axis of this one is still that's passing through the joint, and the axis of this one is translation this way. So they're parallel. All right, these are two joints that are in parallel. Now, the second possible configuration for two adjacent joints, prismatic or revolute joint, is orthogonal. Right. Orthogonal, I'll represent that with this. Now, what's orthogonal? Well, orthogonal is when joint axes intersects at the right angle. Right, pretty, again, straightforward, but you have to just be careful about the definition. Joint axes intersect at the right angle. All right, so think about a revolute joint this way. Right, it rotates in this direction, and then another revolute joint in this way. We should put it. I'm going to put it here. Revolute joint in this way. This is the axis for this one, and this is the axis for this one. So they are perpendicular. Right? Orthogonal, you can think about the reason called orthogonal because we're going to see we're going to also use perpendicular for a different setup. But if the joint axis, it takes some looking at different configurations to get comfortable with definition. Parallel is pretty straightforward. Orthogonal or perpendicular are a little different, and you will see how. But orthogonal is when joint axes intersect at the right angles, right? They're intersecting somehow, and there's a right angle, a 90 degrees angle between them. You can think about, you can replace one of them with a prismatic joint, or you can just use two prismatic joints, right? It can be just even in the previous case. In this case, let's say we have one prismatic joint like this. And the other one as a revolute joint like this. Right? This is the axis for the revolute joint. This is the axis for prismatic joint. Could both of them be prismatic joint? Depending on what is the configuration, what is the motion you're looking for, or what you're trying to achieve. So that is orthogonal. Now, the last one is called perpendicular configuration. Now, the difference between perpendicular and orthogonal is that in both cases, you're going to have a 90-degree angle, but the difference is in perpendicular configuration. Joint axes are in right angle with respect to a common normal, meaning that they're not intersecting. So it can be a distance, like if you think about three-dimensional space, there can be a distance between them. But a common normal going from one axis to another, as long as it exists, right, and both of them has a 90 degrees angle with respect to that common normal, or better to say, they are in right angle with respect to that common normal, then that would be the perpendicular configuration. So perpendicular perpendicular, this represented with this. So joints or joint axes are in right angle. Can do a better angle there, more at least right angle with respect to their common normal, their common normal. Now, what I'm trying to say is that let's assume that we have this revolute joint. Now, the other revolute joint, if this is the axis passing through this revolute joint, the other revolute joint is not exactly on top of this one. The other revolute joint is in a plane that is not on this plane. Let's say the other revolute joint is here. Hopefully I can get it right, drawing it. Let's say it's right there. So there is a common normal between these two of 90 degrees. It's 90 degrees here and it's 90 degrees here. Hopefully you can see that. So these two, right, they are, if you think about that, you can, okay, think about it this way. These two can become parallel if we rotate the second one 90 degrees. If I rotate this one 90 degrees this way, they become parallel. So the difference between perpendicular and orthogonal is that you can think about that orthogonal joint axes are in the same plane. Perpendicular joint axes are not in the same plane, but there is a common normal that both of them have both axes create right angle with respect to. So to help, I can put note. Let's put it this way: two perpendicular joint axes become parallel if one axis if one axis turns, let's put this, turns 90 degrees about the common normal. So this is the common normal, right? This is common normal there. Hopefully it makes sense. Parallel, orthogonal, perpendicular. I don't really have a good example of perpendicular, at least for today. But we'll see perpendicular later on, and I keep referring to it later and later. For now, I just want to be more focused on parallel and orthogonal. Just perpendicular, know the symbol and know the difference between perpendicular and orthogonal. Right? The perpendicular form is a little, there's a gap there. Now, I introduced them using parallel and orthogonal, but remember, orthogonal and perpendicular in so many setups in industrial robots, you will see that they are interchangeable because joints, what happens is that the axes turn out to be in different planes while they still are, they create 90 degree like they're perpendicular, but they turn out to be in different planes. So if they are like this, these two axes, there's usually a gap between them. So they turn out to be, they're orthogonal, and they turn out to be in different planes because of the way things need to be set up. So that orthogonal becomes perpendicular. I don't want to make you so confused. It's just a general procedure, but we'll look at a couple of examples, and I'll tell you from what we see in theory, or at least we can assume that they're orthogonal, but in practice, if you look at the industrial arm, you will see that that orthogonal configuration turns out to be perpendicular because there is some distance between these axes. Again, it goes back to the way they are set up. So let's take a look at some common ones. Now, up to 72 manipulators can be defined for industrial robots using just these three terminologies: the way things are set up, the number of degrees of freedom, the way they move. We're going to be more focused on 5 important ones that are also mentioned in your textbook. All right. I'm going to start with, so let me write it this way. So 5 important, let's say, manipulators. Remember, manipulator is basically just a combination of links and joints and a bunch of other structural elements. Right? We still there is no sensor, there is no actuator, there is no. It's just simply the structure of the arm or the industrial robot. The most common one, I would say, or at least the easiest one that we could to talk about is R revolute parallel revolute parallel. So 3 revolute joints. Let me bring the image here. I have the picture somewhere from the textbook. Bear with me. I will find it. There you go. Schematically, we have 3. I'll make it just small. We have 3 revolute. Sorry, the last one should be P. That's why this should be P. We have 2 revolute joint and 1 prismatic joint. This is the first one. There is a revolute joint. We said we represent revolute joints with kind of cylindrical form, so it rotates this way or the other way, depends on. Usually we go right hand. Connected to another revolute joint and connected to a prismatic joint. Now, if you look at the axes there, this is one axis for this first joint, axis for the second joint, and axis for this third joint. All of them are in parallel, right? The second one is parallel with respect to the first one, and third one is parallel with respect to the second one. So that's how we represent it. R parallel to P. Now, it's commonly known as I put it there, SCARA, which let me put it this way. SCARA arm, the arm, or let me put what does this stand for? I never remember what it is, so I have to look at my notes. SCARA stands for selective compliant articulated robot arm. Sorry, I always make a mistake. Robot for assembly. So it's been used for mainly, these are industrial robots, so a lot of them are actually used for assembly purposes, right? Arm. I can say made or built for or designed for, whatever, designed for, as the name says, assembly operation. Right, so pretty much 3 joints, axes are in parallel with one axis. One joint is parallel with respect to the next one next to it. Now I separated the video somewhere. Show. All right. So in practice, what does it look like? That's pretty much a group of them. If you look at any of those, let's look at the big one, right? There is a revolute joint here, rotation there, and there is another rotation, and then you see the translation, like prismatic joint. And what they do, you can imagine that, especially if you think about a assembly line for electronics, they can pick some part from somewhere, put it, or attach it to another, to part of the, let's say, electronic board. That's one example I can think about. But they're used for assembly. Two revolute joints next to each other, and then the prismatic joint somewhere at the end. Now, we are not talking about end effectors yet, so these have also some end effector. You see, we're just talking about manipulator. Remember back in the first class, previous class, I said we need to add wrist and manipulator, wrist and end effector to a manipulator to have actually a robot, the full.
Excuse me, Professor.
Yes, Lucas.
Is this the same kind of robot that changes tools in a milling or lathe machine? It looks like it has the same degrees of freedom.
It does, but it's not the same. We'll actually get to that. It's one of the common types, but that's more of they call it Cartesian kind of.
Mm-hmm. Okay.
Everything is translational. We don't really see, at least the common CNC machines, that you don't see that much of rotation anywhere. Right?
Mm-hmm. Okay.
Oh, we'll get there. That's probably maybe the last type that I'll talk about. All right. So this is just the general operation to give you a sense of how things work, and what does it look like in actual, I guess, reality. All right. So that's the most common one, SCARA arm. Don't ever ask me again what does a SCARA. Not again. Nobody asked. Don't ever ask me what does a SCARA stand for, because this is probably the first time and the last time I mentioned what does it stand for. Selective Compliant Articulated Robot for Assembly. I'm not going to remember that. Never doesn't stick. But just what does it look like, SCARA? I refer to it as a SCARA. The second type, right? It's an articulated arm, call it, and the general form, at least in theory, is a revolute joint orthogonal to another revolute joint, parallel. This parallel is a little parallel to another revolute joint. We'll talk about it later. So, what happens in this one? Let me bring the picture for this one. I have to find it. There you go. So there is a revolute joint. I have to feed everything in this page. So at least three of them. So revolute joint orthogonal to another revolute joint, and then the last revolute joint is parallel to the revolute joint adjacent to it. Now, let's see how does it work. So if this is the revolute joint base, it rotates the whole thing. This is its axis. Z naught is represented by Z naught here. You can just see that. And theta 1 shows the revolution, the direction, I would say. Now this is the second one, the second revolute joint in this direction, right? Because Z1 represent that. So Z0 and Z1 are orthogonal, right? They intersect at one point, which is somewhere here, theoretically. Right? So that is just, these two are orthogonal with respect to each other. Then we go to the next one. This one is, again, this is the third revolute joint. If you look at the axis of the joint, is parallel to the second one next to it. Now this is, they call it, you can just refer to it as an articulated arm. Let me see if I can put something here. It says elbow, the elbow. Let let's just not put it. The only thing I can think about this is just they are good for industrial robots. You know, the way they are formed, and the most famous one is actually the Puma robot. You might have seen it. I can just put some statistics here. At this reference from based on your textbook, almost 20% or 25% of industrial robots, and this is the number for a few years ago, so things might have changed. Robots are of this kind. This kind. Like Puma. I do not remember what does Puma stand for. I have to look it up, or I'll just leave it to you to look it up. But I think I also put a video aside for this one. These are the things you can actually easily find. All right, there you go. So you have one revolute joint here, right? The base. Hopefully this guy is gonna move it. There you go. So this is the one revolute joint, the base. I actually might be able to. A little difficult, but let's see. So this is one revolute joint here, and rotating this way, and then you have your next revolute joint there. You know, it rotates this way or that way. No, rotates by both directions. This is just agreement that we go in the right direction, but obviously rotates in every direction, positive or negative. And then you have your third revolute joint there. So the first one and second one, right, this rotates, you know, either way. So the first one and second one are orthogonal, and the second one and third one are parallel. All right, I'll just let this. I have to figure out how to. There you go. Obviously, this schematic is not useful anymore, so just clear things up. But pretty much three. This guy is pretty much just really just having fun with that. But Puma is one of them, but generally speaking, you can just refer them as articulate robot arms. And they're very, very practical, actually. You see a lot of them for assembly because they can achieve a pretty good, I would say, coverage or different tasks that we usually want to do in an assembly. And this guy is in a very comfortable closing for a video on YouTube. Confidence. All right, so it's the second type. Now the third type, I'm going to go over, I guess, 5 of them. The third type is you can have, again, I'm just referring to 5. There are multiple configurations that you can have more and more with different joints, the common ones. But these 5 ones are, I guess, the ones that I would say the main manipulators are based on this design. So the third one would be a revolute joint. Let me bring the picture first, and then talk on that. I want to talk about the spherical. It's shrinking. The first image was big, and then. So this is called spherical configuration. Now we have 2 revolute joints orthogonal, and then we have a prismatic joint that is orthogonal with respect to the revolute joint next to it. So it's R, orthogonal, R, orthogonal, P. Now hopefully you see it there. If this is the axis for the first joint, this is the axis for the second joint, and this is the axis for, let me use a different color, third joint. So the first and second are orthogonal, right? They intersect and right angle there. And then the second and third, also prismatic joint, is orthogonal with respect to revolute joint. This is called spherical because pretty much it covers the spherical, I would say, the perimeter. Right? It's pretty good for small robots. Usually they use it for small robots, and the most famous one is a Stanford arm that I did not find a video of it, but you can find photos of that if you search Stanford arm. I'll just say for small uh, robots, usually it's good for small robots, and about 15% of industrial robots like Stanford arm. This is a little old because Stanford came up with different arms, so you might see other things. Let me just look up one and just make sure that you get the right one. This is not what I want to show you, so there you go. Stanford arm. I'll just go to images. There you go. These are pretty. This is a good one, and this also is a good one. Which one I'm gonna open? Maybe this one. I don't know if I can make it bigger. View image, maybe. Oh, that's very tiny. Let me try this one because I want to say something on it. All right. So here is the thing. This one, right? This is the revolute joint we had there. Right? This is the axis. The next revolute joint axis. And then now you see this is the prismatic joint. Forget about the manipulator for now. We don't really end effector for now. And this is the third. Now, here is the trick, right? As I said, the orthogonal and perpendicular are kind of not interchangeable, but depending on how did they set up the R. Now, if this prismatic joint was here, let's say it was here, I'm going to try to draw something close to what it should be. If it was, oh my God, that was bad. If it was here, hopefully I'm not making it more worse. If it was here, then the axis, this axis right there for this, right there, would have been orthogonal, like what we are talking about here. All right, let me bring that up. Ignore what is in the middle of the page. Like what we talked about here. Right? This, the prismatic and the revolute, they were there's an intersection between them. I'm losing the track of my own thoughts. I scratch that. I lost the track of my thought. Let's stick to that. So this is, forget about what I wanted, the point I wanted to make. This is revolute, orthogonal to another revolute, orthogonal to a prismatic joint. Think about just joints next to each other. So this joint right there, this one, I was just going in a totally different direction. So this joint is a revolute joint, right? The whole last piece of this arm, the link, this link can rotate around this arm, this joint, and then this joint, the axis is here. So the two axes are intersecting. So you have orthogonal, 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 but revolute, revolute, prismatic. I just got totally sidetracked by another line of thought. All right, so that's it. Stanford arm, you can look it up. I could not find a good video of that, but I'm hoping that at least the image gives you a sense of how it moves and how it covers the area around it. You can think about it in a sphere. That's why it's called this configuration is called spherical kind of configuration, because it covers the surface of a sphere. It can cover the surface of a sphere using these two revolute joints and one prismatic joint. The fourth one is, let me take a look at my notes to follow, is, let's go with this one. It's a revolute joint, right, parallel to a prismatic joint, orthogonal to another prismatic joint. If I want to draw it schematically, there you go. So this is the schematic of that. Think about the first one, right? Well, we don't need to think about it. You can see it there. The first one is a revolute joint, and this is the axis for that. It rotates around that. Now the second one is a prismatic joint, right? Look at this part. This is the prismatic joint right there. Worst color I could choose. And that is the axis. So they're parallel and on top of each other, obviously. And then the last one that you got is another prismatic joint, and this is its axis. So that prismatic joint and the prismatic joint before that, they're orthogonal. They're in the same plane. There isn't the intercept. 90 degrees angle between them. I did find a video for that. Not a very nice one, but that's the best I could find. And that's also, they refer to it as cylindrical arm. Right? And one thing you see is here it says R2P. That's another way of referring to the configurations, meaning that there is one rotation and there is one revolute joint and two prismatic joints. So that's why they say R2P. Means one R and two P. One revolute, two prismatic. You might see that it's less informative compared to the other way of representing it, because it doesn't tell you exactly how do they stand with respect to each other. Right? Is it parallel? Is it orthogonal? It's perpendicular? Don't really give that much. It doesn't really give that much information. But it's called cylindrical arm geometry because it covers. You can think about it as a cylinder. The revolute joint, the prismatic joint. In this case, the prismatic X goes up and down, and then Y in the I shouldn't use the perpendicular term because we have it as a definition. 90-degree angle with respect to that goes, is a prismatic joint, and you had their rotation because of a revolute joint. Again, assembly lines, you'll see that it actually is very good because they can carry good amount of load. Right? This kind of, I would say, this kind of setup. And they actually, they are there are good number of robot arms that they have this configuration. It's simple to control and operate, and it can carry a low load, heavy loads compared to other ones. I'll let that go a little bit. There you go. This is a good explanation of cylindrical workspace, right? So it can cover, that's why it's called cylindrical. All right. I think you got the idea. Hopefully. And there you go. All right. So a few things about this one. I can say that they're good for medium load capacity. They can carry actually a good amount of load. Robots. What else? You can also go with this statistics based on actually your textbook. So I actually never verify this, but it says it's about 45% of industrial robots are in this form, which is a pretty good uh, portion, I would say. You don't really see these probably in automobile industry. You see a different type over there, more like articulated one. Uh, I would say it's more common there. All right. So fourth one and the fifth one, the last one is, let me bring that. It's a cylindrical type. And that's the one also you see a lot. It's a Cartesian. There you go. So that's the Cartesian form. All the joints there are just prismatic joints. Right? So we can, that will be, actually I'm going to keep it as blue, change this one. That will be prismatic joint, orthogonal to another prismatic joint, orthogonal to another prismatic joint. They're pretty good to carry heavy loads. Right? They can actually carry very heavy loads, and they're used for large robots. Um, about 10-15% of industrial robots, I would say, and they're good for table assembly. Right? You want to do some specific assembly on a table. I'll show you a video of that. They're good for transferring cargo from one place to another. You will see them. This is the kind of configuration that you see a lot in the configuration you see in your 3D printer or in a CNC machine fits into this category. Right? Let me show you at least an example right here. This is from, I guess, sealing equipment, but you get a sense of how things work, right? So the same form of motion you see in a 3D printer, similar kind of motion you see in a CNC machine. So Cartesian, I would say, configuration is common in those forms too. But in terms of if you want to think about assembly, I would think I would say mainly used for heavy load capacity and carry things around, because in this case you see that there is only the one side of this is attached, but it can be both sides and it can actually carry very heavy load. You might see some of these in ports, like taking containers and cargo from big ships into the land, or the other way around, loading those cargoes into, or putting those cargoes into those containers into those ships. All right, it's more focused on sealing process. The first part, just the part I wanted you to see. All right, so this is Cartesian. Maybe I should put this Cartesian. The other one was cylindrical. I have to go and put the other ones too. This one, you can think of this as a spherical. The Puma one, I guess, just say articulated. And the Scara one, I don't know what to call that. It's just a Scara, I guess. There's really no specific name that comes to mind. Just refer to it as a Scara, because that's the most common pretty much form. And that's what defines this. That's the name of the arm. So let's see. So for this one, let's say for heavy loads, right? Good for heavy load capacity and large cargo, large robots. Let's see. I'll talk about cargo later on. Large robots. I have no idea how come the color changed. Large robots. Again, based on your book's numbers, 15% of industrial robots. And last thing I want to mention, they're good for table, top, assembly, and transfer of cargo. Now, the good thing about this one is that I don't want to say as opposed to, but compared to SCARA, that you don't really, you do have a good control over the height using the the last piece, basically last joint, which is a prismatic joint. But this one gives you a better edge, I would say, in terms of, because you can carry more and you can it can handle higher load, and that's what you see in something like a CNC machine when they're pushing a lot of, when you're doing different operations. There's a lot of pressure and load, force applied to the whole system, and these configurations are pretty good at handling a lot of load. All right, these are the 5 most common, I would say, types that hopefully you get a sense of both what they are, how do they operate, and through this we also could get a sense of prismatic and revolute joints and the way they actually are set up for a typical industrial robot, I would say. All right, any question on these ones? Um, if any of these didn't make sense, just let me know. I tried to find some videos. I'll hopefully this weekend I'll also post some of the links to the videos that I showed in the last class and this class on the forum. So if you want to go and watch, or maybe you get into this rabbit hole that watch one video and there's something related to it comes up, and want to explore a little bit, you get some additional, at least I would say initial preference. Let's put it this way, if you want to dig deeper. All right. So, so far so good, right? Now we have to start looking into kinematics of different types of configurations and how can we actually study these motions, right? We looked at different joints, the manipulators, which basically a configuration of joints and links. What we need to do is that we have to kind of figure out how to study them. And to study them, right, we have to set up a couple of definitions, review some terms that I'm hoping they are just reviews, and I'm not hoping, I'm pretty sure that you are totally familiar with everything that I'll go over as a review. But it's just to make sure that we know what we're going to deal with for the rest of the semester, or at least a good portion of the semester. We're going to work with a lot of matrices, so I'm going to warn you from now. A lot of matrix multiplication, in finding the inverse of a matrix, determinant. We're going to use software for that, so don't be too worried about it. But for the beginning of the semester, we're going to do everything manually. Once we have the midterm or exam, we start, actually things get more complicated, and in order to move forward, we're going to use software Mathematica to do the operation for us and do the multiplications for us. All right, so let's put things under, let's just go with unit vectors. Unit vectors and matrix operations. Again, just review. Think about a three-dimensional space, a Cartesian coordinate. I'll just put it right here. Just keep them as right-handed. So I'll say this is X, this is Y, and this is, let's just use lowercase because we're going to talk about local and global. So X, Y, and Z. Pretty straightforward, right? You have unit vector in X direction as I, unit vector in Y direction as J, unit vector in Z direction as K. Some reminders, again, I'll just put things here. I squared, J squared, K squared, these are unit vectors. So this squared is basically a dot product. So it becomes just one. You have magnitude of 1. and direction is along each axis. Cross product I cross j. Let's put I cross. Let me do it all the way in the right direction. J cross k and k cross I. Three things at least I can think about. I don't know if you remember those cross products and the result of that, but I can just give you this that I usually use. I, J, it's kind of cheating. I cross J, go along the arrow, it becomes K. J cross K becomes I. K cross I becomes J. Same process if you want to go inverse. Let's say J cross I. J cross I becomes minus K because you're going in the opposite direction. K cross J becomes minus I. What else we can do? I cross K, I guess. I cross K becomes minus J. Dot product of these, I dot I is, what is I dot I? Can someone tell me that? Well, no, that's easy. I dot J. I dot J.
-1.
Nice try. Another opinion. I dot J is a dot product, right? What was the dot product? Dot product was, let's
Sorry, it's K.
all right. Dot product is A and B, right? And the angle is alpha. So A dot B is AB cosine alpha. And it's just a dot product. There's a reminder put here. Dot product. Now we have two vectors, I and j. So I dot j would be ij. I is 1, j is 1, so multiplication would be 1. Cosine the angle between these two. What is the angle between I and j?
90.
90. So cosine 90?
0.
0. There we go. So I dot j, the same story, j dot k, same story, whatever, k dot I. Right? They all are 0. So follow definition for dot product. All come to you. Old knowledge probably. That's why I'm just mentioning this here. Important operations that we're going to use a lot: matrix operation, matrix multiplication, finding inverse of a matrix, and determinant. So matrix multiplication, let me go with this. Matrix multiplication. I'll just go with 3 by 3 matrix and give it to you, but just as a review, you again know that for 2 by 2, but 3 by 3 is a more common one that we're going to use in this course a lot. So if I want to write it, I want to make my life difficult and write it in, like, let's say letters A, B, C, D, E, F, G, H, I. We do a lot of matrix multiplication, so I guess it's worth it to just put it here. J, K, L, M, N, O, and let's say P, Q, R. So let's do that operation. First row from the first matrix multiplied by the first column of the second matrix gives us the first element. So A, J plus BM plus CP. first row of the first matrix multiplied by the second row of the second matrix gives us the element on the first row, second column. So that becomes AK plus BN plus CQ. Third one, I'm just going to clear this a little bit, give me some room there. Keep it right there. First row, third column, multiplication dot product between these two, basically if you think about them as vectors, gives you the element on the first row, third column. So that would be AL, wrong color, AL plus BO plus CR. Right? Hopefully everybody follows these. Now go to the second row. So we go to the second row of the first matrix multiplied by the first column of the second matrix. That gives you the element on the second row, first column of the result. So that would give you DJ plus EM. I can write it better again. Plus EM plus FP. FP. Second row, second column gives you the second row, second column of second row of the first matrix, second column of the second matrix gives you the second row, second column of the result or the final matrix. So this gives you DK plus EN plus FQ. Last one, DL plus EO plus FR. Third row from the first matrix, multiply the first column of the second matrix, GJ plus MH, or let me just go with HM, the same at least, doesn't really matter, but just to IP. Then third row, second column, multiplication GK plus HN plus IQ. And the last one would be GL plus HO plus IR. And this is a 3 by 3 matrix. This is a 3 by 3 matrix. As a result, the multiplication would be a 3 by 3 matrix. We do a lot of 3 by 3 multiplication, and I guess in a few weeks we'll also get to 4 by 4. So I'll leave it to you, and I'm going to go over the example of 4 by 4. We'll see pretty much the same process. Hopefully you remember matrix multiplication. If you don't, review that. Right? Determinant of a matrix, right? I can just put it here. Determinant of a matrix. For a 2 by 2 matrix, let me see if I have an example so I can go actually over. Yeah, let's just go as a general form. For a 2 by 2 matrix, if you say A, B, C, D, right? Let's say I call this matrix A. So determinant of A would be AD minus BC. Right? Multiplication of these two minus these two. So we go multiply these two and multiply minus multiplication of these two. Now if it becomes bigger, right, as 3 by 3 matrix, what happens there? So we have, let's say it this way, if A is A, B, C, D, E, F, G, H, I, okay? Determinant of A would be A multiplied by, eliminate the row and column that element is part of, EI minus FH. And then minus B just give you the general form, but let me just not explain it. I'm hoping that you know. I'm just doing a review. So B, you eliminate the row, first row and the second column, since that row and that column, the summation of those two becomes 3. First plus 2 is 3, so you have minus there. B times DI minus FG plus C, as first row, third column, so 3 plus 1 is 4, minus 1 to 4 is 1. C times DH minus EG. Right, so this is the determinant of a 3 by 3 matrix. All right. I don't go over an example. It's too simple. Finally, the inverse. Last thing, I think it's pretty practical to know inverse of a matrix. Right. Let's do it for a 3 by 3 matrix, I guess. Let's do that with example. So if A is, well, the general form is that if you have a matrix A, right, A for A 3 by 3, A inverse is basically 1 over determinant A, a matrix. Let me write it this way. A 3 by 3 matrix, and I call these A, I, let me go with a good notation so things don't get confusing. Let's do a, this was the typical ADJ 1, ADJ 1, 2, ADJ 1, 3, ADJ 2, 1, ADJ 2, 2, ADJ 2, 3, ADJ 3, 1, ADJ 3, 2, ADJ 3, 3, where ADJ IJ is the determinant of a 2 by 2 matrix when removing row I and column J of A. Right. So see if I have an example. Maybe this. I should leave it to you. I'll put an example here and give you the answer. You do the calculation. Example. Find the determinant of A. I draw on my notes somewhere. A inverse. Why they say determinant? Find the inverse of A and that A would be 1, 2, 3, 0, 1, 4, 5, 6, 0. And the answer would be, it's good for you to practice, I guess. A inverse is So I got 1 0 5 2 1 6 3 4 0. All right, do that for yourself and figure it out. You find the determinant 1 over determinant. Obviously, the main assumption we make here is that the determinant of the matrix we're trying to find is inverse should not be 0. If it's 0, then 1 over determinant it doesn't make sense. So the main assumption should be that the determinant of A is a non-zero value. Once you find the determinant, 1 over determinant times that matrix. How to form that matrix? Right? For instance, A is an example for this A matrix. ADJ11 is the determinant of eliminating this is 1 6 4 0. Let's see if I got the right number. It's going to be 1 0 minus 24. So it becomes minus 24. Right? Another example, ADJ, let's say 1 2 with the determinant of eliminating the first row, second column. So you'll get 2 6 3 0. Right? And that'll be 2 0 minus 18. I continue that to find all the elements of that 3 by 3 matrix. Find the determinant of A, 1 over determinant multiplied by multiply all the elements with that. You should get this value for the A inverse. All right. We'll talk about some other, I would say, notation in the next class at the beginning, and then we'll dive into how to find the rotation matrices and how can we use that to look into rotation kinematics. We'll stop here. So if you have any question, folks, this